Hey, mathletes. What we're going to talk about here is area between curves again, but this time we call it part two. This time what we're going to have is our bottom curve won't be the x-axis. Our bottom curve will be a different function other than the x-axis. Good news is it doesn't actually make things that much more difficult. Okay, let's take a peek here. So again, our goal today is to determine this area between two curves, and our second curve or function won't be the x-axis. Okay, won't be that bad. So here we go. Determine the area enclosed by y is equal to x plus 1, y is equal to 9 minus x squared, x is equal to -1, x is equal to 2. Whoa, wait a minute. I thought you said a second ago this wouldn't be too bad. I'm not lying to you. It just looks worse than it is. Okay, here we go. As soon as we draw this, you'll see what I'm talking about. Okay, x plus 1. Well, let's go back, and what I remember way back when is that my y-intercept is 1 and my slope is 1. So this one here looks more or less something like that. Let's call that y1. Okay, 9 minus x squared. Okay, so 9 minus x squared. So I've got an x-intercept over here at -3. I've got another x-intercept over here at +3, and my y-intercept is somewhere up here at 9. Okay, so this one does something more or less like this. All right, and then that's y2, we'll call it. And then we've got x is equal to -1. Okay, so where is -1? Let's be really precise here. Well, -1 is right where that x-intercept is on that graph. So that's that right there. There's x is -1. And when x is 2, well, x is 2 is going to be, somewhere over here. Right there. So there's when x is 2. All right, friends. So now we've got to find that region. Okay, it's nice because our top function, y2, is always the top function. And our bottom function, y1, is always the bottom function. So let's go and find this area. So our area is equal to lower bound -1, upper bound 2, top function 9 minus x squared minus lower function x plus 1 and dx. Okay, now before we take the antiderivative of that, let's absolutely simplify this down. So we get 9 minus x squared minus x minus 1 dx. And now we're going to simplify that down to, what are we going to have here? Minus x squared minus x plus 8 dx. Okay, so it's not that bad of a function to take the antiderivative of. Okay, here we go. Let's take that antiderivative. So we're going to evaluate this one. -1/3 x cubed minus a half x squared plus 8x, evaluated from -1 to 2. And again, we know what to do here. So I'm going to move a little bit to the left. Is now we sub in these values. We're going to sub in the 2. Subtract. Again, brackets. Sub in the -1. And at this point, this is where, again, we could do this without a calculator, and it's good practice to do it without a calculator. But at this point, friends, we're able to just pick up our calculator because we have one. And if you do that, you're going to find that we get an area of 19.5 units squared. Okay, so again, what we're going to see here is the most difficult part of these questions, in a lot of cases, isn't taking the antiderivative or finding the definite integral. It's going to be in just drawing the curve. Can I remember how to draw these things from way back when? Okay, that's where some of us will struggle the most. Okay, let's try another couple. Determine the area between y is equal to x plus 2 and y is equal to x squared. Okay, so again, first thing we're going to do is we're definitely going to draw this one. So what have we got? Well, y is equal to x plus 2. All right, so again, I've got a y-intercept at 2. And my slope is +1, which means I'm going to have an x-intercept at -2. So there's that one. Let's call that y1, just like that. And then y is equal to x squared. Well, x squared, of course, vertex is down here, and it's going to come up like this, and it's going to come up like this. Okay, but we want the area between these two things. We're looking for this region. Let's do hot pink. We haven't used awesome hot pink in a while. Well, friends, what do we need to do if we want to find that region? Well, we definitely need to then find these 2 points of intersection. That's the first thing we're going to have to find. So let's go and find these points of intersection. Points of intersection. So again, it's not about the difficult part's not again going to be taking the antiderivative or the definite integral. It's going to be finding all the parts leading up to it. So if I want to find the points of intersection, well, that's where y1 is equal to y2. So that's where x plus 2 is equal to x squared. So that's x squared minus x minus 2. Let's factor that thing, x minus 2, x plus 1. So what do we have? Therefore, our points of intersection will be when x is 2 and x is -1. Now, I don't really care what the y values are because I'm going to take the definite integral with respect to x. Now, there will be a time where you might have to take the definite integral with respect to y, and in which case we would want to know those y values. But for now, I don't care. These are our bounds. Good enough. Okay, so now, friends, let's go and take the antiderivative of this thing. So I'm just going to switch off hot pink here. Our area then, our bounds are from -1 to 2. Our top function was the linear, which was x plus 2, minus our lower function, x squared dx. Okay, and from here, we can, I think I'm going to rearrange this, right? Like we could take it right there, but it just kind of looks strange and foreign to me to have it written like that. So I'm going to simplify it to that. Okay, and let's take the antiderivative of this. Well, we know that's -1/3 x cubed plus 1/2 x squared plus 2x, evaluated from -1 to 2. And now, friends, all we got to do is sub those values in. And here we go. -1/3, 2 cubed, just like that, just like that. And do it all over again, okay? And so again, there's lots of places in here where simply just calculating, evaluating this value can make errors, right? You could see why. And so at the end of this, friends, pick up your calculator and give it a go. But what you're going to find is you're going to get 9/2 units squared, or 4.5. Okay, so there's another one. Not so bad. Again, I find usually it's simply just, can I even graph this, right? That's the thing that sometimes just gets in the way. Can I even graph this? Okay, friends, let's do one more. All right, let's go back to trig, right? Okay, determine the area between sine x and cos x. Oh boy, sounds like fun. Okay, so from 0 to pi12. Okay. So sine x, let's draw it in blue. So sine x, I'm just going to stop at pi there. And we know pi12 is that relative maximum right there. And there's 0. So there's, and I know that keeps going, but I'm just going to stop there. That's y1. Okay, let's go pretty green. Okay, cos x we know starts up here at a max, and it's actually going to come down through pi12 and comes down and has a min right there. Okay, and again, I know that keeps going, but I'm just stopping there for the sake of simplicity. Oops, that's a 1 right there. Why did I write a 0? Okay, so we want to know this region in here bounded by pi12. So we want this region right here and right here? Well, again, as soon as I see this, friends, I'm going to say, okay, well, couple of things. We need that point of intersection that's right in the middle there. Okay, that's going to be something really, really important. And then I also notice that my upper function and my lower function, y2, switch, right? So we're going to break this up into two areas. So we're going to find area 1 and area 2. Okay, so that's something to consider as well. Now, here we go. First off, where do these two things intersect? Well, a couple of different ways to think of it. Again, where do these guys intersect? So our point of intersection. Well, our point of intersection is where y1 is equal to y2, which is where sine x is equal to cos x. Well, there's all sorts of ways you could do this. You could just start thinking of your unit circle right now. You could divide both sides by cos x, and then you get tangent x is equal to 1. Well, where is tangent x equal to 1? Well, tangent x is equal to 1 at pi quarter. So our point of intersection right there is pi quarter. Okay, so now what we're going to do, friends, is we're going to go and find our areas. So I'm going to find area 1 first. I'm going to call this one here area 1. And I'm going to find this one here. I'm going to call it area 2 second. So here we go. Area 1. Area 1 is equal to the definite integral from 0 to pi quarter of our top function, cos x, minus our bottom function, sine x, dx. Area 2 would be from pi quarter to pi half of our top function now would be sine x, and our bottom function would be cos x dx. Just like that. Oops. Dx. All right. And so now, friends, all you need to do at this point is just take the antiderivative and then evaluate it on your bounds. So area 1, so the antiderivative, well, the antiderivative of cos x is sine x. The antiderivative of sine x is negative cos x, so we get plus cos x evaluated from pi quarter to 0. Area 2, well, again, the antiderivative of sine x is negative cos x. The antiderivative of cos x is sine x, so negative sine x, evaluated from pi quarter to pi half, just like that. Okay, and so now what do we get? Well, we just sub in these values. So we're going to get sine of pi quarter plus cos of pi quarter minus sine at 0 plus cos at 0. So area 1, sine at pi quarter is root 2 over 2. Cos at pi quarter is root 2 over 2. Sine at 0 is 0. Cos at 0 is 1. So area 1 then is root 2 half plus root 2 half is just 1 root 2. So root 2 plus 1. Okay, so there's my first area right there. Okay, coming over here to area 2 then. Area 2, again, we're just evaluating this thing. So we're negative cos x at pi half minus sine at pi half minus, I'm getting a little squished here on the corner of my screen, minus cos at pi quarter minus sine at pi quarter, like that. Okay, area 2, cos at pi half is 0, sine at pi half is 1, minus cos at pi quarter is root 2 over 2, sine at pi quarter is root 2 over 2. So area 2 is negative 1, and then in here we've got plus root 2 after we simplify that thing down, because that would be negative root 2, and then the negative makes it a positive. So there's our two areas. Perfect. And let's go ahead and add these two things together. So area total is equal to area 1 plus area 2, which is equal to area total root 2 plus 1 plus minus plus root 2. And guess what? We end up with 2 root 2, just like that. Okay, so there you go, friends. There is finding the area bounded between two curves.